problem number 7 in group theory, revolving around Sylow's theorems. We have let G be a finite group and P be a prime divisor of the order of G. For A, suppose N is a normal P subgroup of G. Prove that N is contained in every P Sylow subgroup of G. Okay, so we'll prove A. And okay, we want to prove that. So okay, first of all, we're assume that N is a normal P subgroup of G. And we want to show that it's contained in every P Sylow subgroup of G. Okay. We're going to let Q be a Sylow P subgroup. I think the question should say Sylow P subgroup instead of P Sylow subgroup. Let Q be a Sylow P subgroup of G. Okay. Then by Sylow's theorems, there exists a G in G such that N is contained in GQ G inverse. And okay, so we want to call GQ G inverse something. So I'm going to say let GQ G inverse equal P, and remark that P, okay, it's annoying, P is a Sylow P subgroup of G. Okay. So we have that N is contained in some Sylow P subgroup of G, but we want that it's in every Sylow P subgroup of G. So I'm going to use this idea again, but I suppose what I'll do is I will let S be any Sylow P subgroup of G such that, maybe not such that, we'll just let it be any Sylow P subgroup of G. So this is my general Sylow P subgroup that I'm working with, and by the same properties, okay, no, since every Sylow P subgroup is conjugate with every Sylow P subgroup is conjugate with every Sylow P subgroup, there exists an H in G such that, let's see, we have P is equal to H inverse. Should I use P here? Or should I be using another letter? No, this is probably fine. Okay, so let's see what we have. We also know that since N is normal, we have that Gn G inverse is equal to N. Hence, from N subset EQ P, that should be an N, not an H. So from this inclusion, we get Gn G inverse subset EQ G P G inverse. But I don't want to conjugate by G, I want to conjugate by H. Okay. Because I said PH, okay, so I see where I want to use this. I should fix this guy to, let's flip it, let's put S equal that guy. Okay, so we get this inequality where we know that N equals this and S equals this, our general guy. So let's see if this makes sense. So we assume N is a normal P subgroup of G, let Q be some Sylow P subgroup of G, then by Sylow's theorems there exists a G in G such that N is contained in the conjugate OG, and then we define this to be P, and remark that P is a Sylow P subgroup of G. Let S be any Sylow P subgroup of G. Since every Sylow P subgroup is conjugate with every Sylow P subgroup, there exists an H such that S is equal to this guy. We also know that since N is normal, we have that guy. Maybe I'll even say, I'll use H here because that's what I use later. And hence from this inequality, which is the thing we had first, if we conjugate by H on both sides, we get that N is contained in every. Thus, N is contained in every Sylow P subgroup of G. Okay, and that's A, I believe. Okay, then just part B remains. Part B says, prove that the intersection of all the P Sylow subgroups of G is the largest normal P subgroup of G. Okay, so let's look at that. Let I be the, can I use big cap? Is that a thing? Yeah. Be the intersection of all the Sylow P subgroups. I think this is a fine notation. All the Sylow P subgroups. Yeah, there we go. Is there a way to, maybe I'll put this in math mode. Okay, so we let I equaling the intersection of all the Sylow P subgroups of G, and we want to show that this is a P subgroup. So since each Sylow P subgroup of G is a P subgroup, the intersection of each one will still be a P subgroup. Okay, we want to justify why it's normal. To show that I is normal, consider, let's see, we'll consider, conjugate it, consider this guy, which is equal to this guy earlier. Okay, slash right. I'll put these in left parentheses. Okay, but we can just bring these inside the intersection to get this guy. So to show that I is normal, consider this guy for, I guess, G and G, I'll say, for G and G, and we will observe that the set of these guys that we're taking the intersection of, where P is in the Sylow P subgroups of G, this set, all right, so what do we know about this set? Yes, okay, observe that, okay, the set of these guys is precisely the set of all Sylow P subgroups of G, since Sylow P subgroups of G are conjugate, and conjugates of Sylow P subgroups of G are still Sylow P subgroups. All right, and that's a lot of words. Let's unpack that. We're saying that essentially, if you conjugate a Sylow P subgroup, you still have a Sylow P subgroup, and every Sylow P subgroup is conjugate with every Sylow P subgroup. So the set of this guy, these guys, is just the set of Sylow P subgroups, which is just P, or it's just I. Essentially, this conjugate guy is equal to P, and so this entire thing is just equal to I, which, let's spell that out on the LaTeX. Let's see, where was I writing this? Writing this here, so we want to grab this last guy, and we want to go hence this is equal to, well, it's the same thing with just P, which is equal to I. Yes, whoops. Thus, we showed that this guy is just equal to I. Therefore, I is normal in G. I is normal in G, which is the second thing we wanted to prove. So we have that it's normal, and it's a P subgroup of G. We just want that it's the largest P subgroup of G, which we're going to use by part A. By part A, we know that every normal P subgroup of G is contained in every Sylow P subgroup of G. Thus, okay, so let N be a normal P subgroup of G. Then we have that N is contained in I. Whoops, N is contained in I. So essentially we have that every normal P subgroup of G is contained in the intersection, hence the intersection is the largest normal P subgroup of G. So we'll just write that last sentence. Therefore, I is the largest normal P subgroup of G.